Okay, I'm sure many of you have already seen this because it was rather widely announced, but the OpenAI team has announced a new model that produces pictures instead of text. So as you can see right here, on the left, you'll always see like a half a picture. And on the right is the ground truth. So they took this picture, they simply cut the bottom half right here, and then they let the model sort of imagine what they cut away. And what it comes up with is pretty cool, I have to say. Like, look at the birds. Like, this is just awesome. But the special thing about this isn't that it simply completes pictures. The special thing about it is it does it one pixel by pixel. So basically, it goes at this pixel right here and asks, okay, what's that pixel? And then what's that pixel? And then what's that pixel? And so on. So it is basically like a language model, but for pixels, in that it goes over the images in order, basically like this, or like always from left to right, left to right, left to right. And it has no clue of the spatial relations between the pixels. It needs to learn that by itself, as opposed to a convolutional neural network, which is specifically designed such that if you want to predict this pixel right here, then it's specifically designed to say, okay, the most important information is probably around that pixel, and then some like other important information is wider around that pixel. So CNNs are built with this in mind, whereas this model right here, which is also known as Image GPT, doesn't have any of that. It's simply a transformer model that goes over these pixels one by one. And we'll see how that's done. There are some more examples right here. Particularly cool is the cat. And you see that there's the beginning of this little white thing right here, which is this card. And the completions of the model are yes, very interesting. The model can, of course, as a language model, can also sample by itself just random images. You sample them once through, and this is what it comes up with. So these are pretty good quality images for a model that just produces one pixel by one pixel. Now, this idea of one pixel by pixel isn't new. This has been around before, but the investigation here is basically how far can we push these generative models for pre-training?
Hi there, this is Yannick from post-production. I've realized that I've forgotten to even read the name of the paper. So it's called Generative Pretraining from Pixels by Mark Chen, Alec Radford, Rowan Child, Jeff Wu, Hewon Ju, Prafula Dariwal, David Luan, and Ilya Sutskever. And since Henry AI Labs has already made a video on this, this video is going to be more of kind of a rumble rant about what I find interesting about the paper and some thoughts about it, rather than like a classic explanation. I hope you still enjoy that.
So what you saw on the right this isn't the final result, the supposed result. This is simply the pre-training task. Now, it's fun to look at it, but the actual objective of the paper is the following. What if we pre-train on a large data set to generate good images like these, or to complete images like these? And then we fine-tune on a classification task. And the answer is here, they say, on C410, we achieve the 96.3% accuracy with a linear probe outperforming a supervised wide ResNet, and a 99% accuracy with full fine-tuning, matching the top supervised pre-trained models. An even larger model trained on a mixture of ImageNet and web images is competitive with self-supervised benchmarks on ImageNet, achieving 72 top 1 accuracy on a linear probe of our features. So the goal here is that you have a data set that you want to train a classifier on. So usually you have a data set, and the data set has images, and you put them through like a convolutional neural network, and then you have to classify the image into one of, I don't know how many classes. So on CFAR10, that's 10 classes. On ImageNet, it's 1,000. And the data set is these images together with these labels. Now, the idea of pre-training is that you somewhere have a bigger data set that is sort of similar to the small data set, but yeah, it's similar enough such that the network could learn something. So what you want to do first is you first want to take the large data set, train this network right here, and then in a second step, fine-tune the network on this smaller data set. And you sort of hope that what you learned from the large data set right here transfers over a little bit of knowledge. You already have a little bit of knowledge, and you can make better use of the data that you have right here. Now, the question is, how do you do this pre-training? And of course, this has a long tradition, well, long for maybe 2 or 3 years right now in the language community, where people, they pre-train these large models, like we've just seen GPT-3 or BERT was one of them. They pre-train these large transformer models on text, and then to fine-tune them on classification tasks for text. And that's what this paper is doing right here. They pre-train a transformer that is a GPT-2 scale model. They pre-train it on image generation, and then they fine-tune it or transfer learn it to classification tasks. And the point of the paper is to say that, like in text data, we have made pretty good experiences with doing this, with pre-training a generative model and then fine-tuning on a classification task. While so far in images, all we've ever done is we've pre-trained these pre-training tasks usually is a classification task, or like a self-supervised task with a contrastive loss or something like this. What they're doing new is the generative modeling as a pre-training. And again, this isn't like entirely new, but they show that if you throw a lot of computers at it and lots of data and a big model, then that can work equally well to these self-supervised tasks. So their model, as I said, is pretty simple. They take an image and they unroll the image. Now, a fully unrolled image on, let's say, ImageNet has 224 squared pixels, and that times 3, right? Because you have 3 color channels. That's too large, even for an OpenAI supercomputer. So what they do is first they downscale the image. So they downscale. It's not as drastic as here, where you just get a 3x3 image, but they do downscale it to like a 32x32 or a 64x64. Then they unroll it, which simply means they go through the image like this and make a sequence out of it. Because their models are naturally made for text sequences, they simply put the image into a text sequence. They further simplify this by reducing the 3 color channels to a single one. So they have their own color representation, and basically, they reduce the 3 color channels to one channel that simply indexes the color in their color representation. And they say it's still pretty good, it's pretty faithful. So ultimately, they end up with like a 32 squared length representation of their image. And then they do one of 2 things. They either do autoregressive generative pre-training, which is the sort of GPT-2 style pre-training. And the idea here is that you always want to predict the next pixel of a sequence. So you can see right here, that's the sequence that you, that's the sequence that you input, and you always want to predict what is the next pixel. And in this case, you see that we've already predicted everything. Here we've already predicted everything up to this red pixel. So you want to know what's this next pixel, this thing right here. What's this going to be? And the diagram here basically shows you how the attention flows. So every position in this transformer, and if you don't know what a transformer is, I have made a video about attention is all you need, where these are explained. But briefly, every position here can sort of send information, only in one direction so you train all of these in parallel. And when you predict this pixel right here, you only want information from whatever was before that pixel. Otherwise, the model could cheat, right? Otherwise, the model could simply learn to copy over the value. But the attention pattern here is simply to show you that this is autoregressive and it's in one direction. So you always want to predict the next pixel. And then from all of this, you want to predict the next pixel. And then from all of this, you want to predict the next pixel. This is in contrast to this objective here that comes from BERT. And I've also made a video on BERT. What you do in BERT is you simply take that image and you block out 2 of the pixels, or many of the pixels, and you simply ask your network to reconstruct those pixels, okay? And now you can see the attention flows in all direction. BERT, the B stands actually for bidirectional. So this is the contrast to the autoregressive pre-training framework. Now, these 2 things have been applied in text, both. The autoregressive is usually, it's easier to actually make it produce something, like we saw producing these images, because you can always just predict the next pixel and then the next and then the next and then the next. Whereas in BERT, it's a bit more unclear how you would produce things in a consistent manner, because the predictions of these 2 pixels right here, they are independent. It's one forward pass and then both of these are predicted. But other papers have tried to solve this, like this, not XLNet. I forget its name. It's something with an X. And yeah, but these are the 2 objectives they look at, and it turns out they sort of trade off a bit. They work equally well, or a bit better and a bit worse, depending on the task. So once they have done this, so they simply feed images, and you will notice that you don't need any labels for this. So what you'll do is simply input an image and then simply take away half of it like this, and then predict that pixel, and then you want to predict that pixel, and then you want to predict that pixel, right? That's all, like you do with text. And in BERT, you simply input an image, cross out pixels, and then predict them. So you don't need labels for this. And that's why you can do it with this big data set. And you can do it in an unsupervised fashion. So you can just crawl the internet for images and just feed this into there. And it will sort of learn to produce these images. Now the question is, if you learn to produce these images, does that help you for classification? And they have 2 methods of assessing this. The bottom one here is the fine-tuning method, where you simply, so this is supposed to be the representation you learn in the different layers of the network. So this is supposed to be this thing right here. What you'll do is you'll simply fine-tune. That means on top of this representation, you add a classification head that has 2 outputs, cat or dog, and you train this entire network on your small data set that we discussed before. So you train the entire network, all of the parameters. This is called fine-tuning. In contrast to that, what you can do is you can simply, and this is the easy way, you can simply add this classification head with 2 outputs and then only train this classification head. And that won't perform as well, but it gives you sort of a better idea of how good is the representation that this network right here learned. And on top of that, so if you spin this idea further, you can actually go and do this at any intermediate layer right here. So you can forward propagate until layer 2 right here, and then here you add your classification head into the two classes, and you only train the classification head. That being said, you can also do this with fine-tuning, but in this case, this is called a linear probe, and it is often used to assess how good a representation in intermediate layers is. Whereas what it actually does is assessing how linearly classifiable a representation is, which isn't the same as how useful or how informative, but it is one way to assess these things. Okay, so these are the two things they assess. All right, so as for data sets, for CIFAR-10, they use like CIFAR-10 and CIFAR-100 as data sets, and the STL-10. And there you have to keep in mind that the pre-training is done on ImageNet for those. So you pre-train on ImageNet without the labels, and then you transfer learn or fine-tune or linear probe on these small data sets. Whereas later we're going to look at ImageNet, and there the pre-training, as I understand it, is done on ImageNet itself, but also a wider collection of 100 million or so images from the web, from the internet. Okay, so as you can see right here, this is what happens if you do this linear probing. And you can see it works pretty well. So you get like a 95-96% accuracy with linear probes. This is very powerful. So it's not easy to get 96% on CIFAR-10. I mean, current state of the art is like 99%, but still 96% is pretty good. And this is the entire network. There is this big giant network that you input your image into, and then there is this one linear layer that does the classification. And all of this right here has not been trained with classification in mind. It simply has been trained to reproduce images. It hasn't even been trained on CIFAR-10 as far as I understand. It's been trained on ImageNet. So this is to stress how cool or how significant this result is, basically, that just a linear probe on top of that will give you such a good accuracy. And the second thing that is obvious right here is this bottom axis is the layer. So this is the layer where they attach the linear probe. And usually if you pre-train a network with a classification task in mind, so you pre-train it with the labels or maybe even without the labels in a self-supervised way or something like this, usually the last layer has the best representation for classification. But here the special thing is that the intermediate layers in the middle have the best representation. You can see that the representation quality in terms of linear probing falls off as they sort of it falls off as they go into higher layers. And this is consistent across the data sets, as you can see. And the idea here is, or the way they interpret it is, that if you have an image right here, and you've blocked part of it, so you've blocked this and this, wrong way around this. So, no. You've generated everything, and now your task is to predict the next pixel, right? So you train to predict this next pixel right here. And the idea is that as you put the image through the network, what it will do is sort of, since the first layers, they're going to be similar to a CNN. They're going to be doing some low-level feature transformation thing, right? But also the last layers, they're going to really care about what's the exact pixel that goes here, right? Since it's their job to do that. They're going to care what color does it need to have, what exact luminosity and so on, how does it fit in with the previous pixels and so on. So that's also good, but it's not just low-level information and consistency with other pixels or something like this. At some point, if you want to generate consistent images, and we saw that this model can generate consistent images, at some point there needs to be some kind of a notion of the global information in the picture, right? Because the images are consistent throughout. So there needs to be some notion of what is in that image as a whole. And that's the exact information that we need for classification. And the only way that could actually be is here in the middle, since that's the place. So the hypothesis is that these models somehow learn a higher level representation of global information somewhere in the middle before they then specify that information again down to predict the actual pixel. And that's why the best representations for classification are in the middle. So this is actually the interesting finding, or one of the interesting findings of this paper. I mean, it's cool that they can reach a good accuracy, but to recognize that maybe in these generative models, they have some intermediate stage where they represent the global information, and that will actually make the best representation. Okay, the second cool thing right here is that you can see they have different sizes of models. So the iGPT-L, I believe, is something like 60 layers. Then this is like 48 layers, and this is 32 layers. We don't really. So these are on the scale of GPT-2, either a little bigger or a little smaller. It's not like GPT-3 scale where you need a ginormous supercomputer, though they do a lot of computation. But this still sort of fits within hardware of a standard size and not like exascale. What's interesting right here is that you can see the larger models, they reach a lower validation loss. So here is the validation loss. The larger model, if you train them on, so these checkpoints here are always after the same amount of steps. The larger models do reach a lower validation loss right here, as you can see. So this is the large, this is the medium, this is the small. And also, you can see that on this axis, the linear probe accuracy. So this is whenever you go and you find the best intermediate layer for linear probing, you probe it and you record the accuracy. So you can see a general trend. As your validation loss goes down, the linear probe accuracy goes up. So there is a connection like it is in text models. In text models, there's a connection of the perplexity of your language model and the quality of the representation you get for downstream tasks. In this model, it seems to be the exact same thing. There is a connection between reaching lower validation loss and reaching a higher performance on classification. So that's one interesting thing, the general trend to the upper right corner. The other interesting and even arguably even more interesting thing is that if you look at the same validation loss, so at this point, all of these models have the same validation loss, yet still the bigger model is better, right? You can see right here, the bigger model outperforms the smaller model, even though they have the same validation loss on the image modeling task. And this is also something that OpenAI in their text papers has stressed, that the larger models, they seem to be somehow more capable of forming good representations, even if they have the same loss. So again, this could just be sort of a training data, better training data remembering thing. And when I said that in GPT-3, I didn't actually mean explicit remembering of training data. I meant kind of a fuzzy remembering of training data. I formulated that in the comments, but I feel a lot of people have misunderstood me there. Here, I think it's a much harder to estimate what's going on. Also, since image pixels, humans don't have a super good model on image pixels in their head as we have about text. As you can see, if you then fine-tune, so for now we've just do linear probing. If you fine-tune these architectures, then you reach like a 99% accuracy on CFAR10, which is on par with the best models that we have. So GPipe is supervised, pre-trained on ImageNet, but also, I guess, uses a bunch of data augmentation, while these image GPT it uses minimal data augmentation, I think. They simply random crop a little bit, and that's about it. So they also experiment around with this BERT objective. So until now, this was all this autoregressive objective, and I feel the OpenAI people are a bit more of a fan of the autoregressive objective, just given what they've done so far in their papers. And you can see here the comparison of the two objectives on C410 and on ImageNet. Again, C410 is pre-trained with ImageNet, and ImageNet itself is pre-trained with like a larger collection of images from the web. All the pre-training is done without labels. Now, the blue is what you can reach with a linear probe, and the orange is then on top of that what you can reach by fine-tuning. Okay, so no linear probe, but fine-tuning. Well, I have to say that the fine-tuning is always done at the end. So even though the linear probe can be attached anywhere in between, and it's often useful to do that, as we saw, because the in-between layers are the best. They say they tried fine-tuning also from in between, but it always worked out best whenever you fine-tune, you take actually the last layer. So that kind of gives you an idea that the model is then, it's sort of, what seems to be important is this coming up with the higher level representation. And then once you fine tune, you're probably able to push that representation through to the end because of your training signal. But if you hadn't done the pre-training, you wouldn't even have that higher level representation. And then the signal, I guess, is not strong enough to backpropagate through the whole model. It would be very interesting if they do this linear probe analysis again after they fine-tune the model. And to see if then still it is the intermediate layers that have the best representation, or if now the best representation in a linear probe sense shifted towards the end. I'm going to guess it's shifted towards the end, but I sort of want to even see if the accuracy of the linear probe in the middle, does it keep the same, right? So does the curve go like this? This is the linear probe when you simply pre-train, right? This is the linear probe accuracy. The question would be, does it change to be like this, or does it change to be like this? This is supposed to be the same at the end. So basically, does it stay as good as it is, but simply get better at the end? Or does the representation, like in this curve, does the good representation now shift towards the end and leave the lower layer with even more capacity to do some low-level stuff? Yeah, maybe they've done this. I haven't seen it. So, and as you can see, these BERT and autoregressive objective, they sort of trade off. So the BERT, it tends to do poorly in the linear probe setting, but then it catches up during fine-tuning. In C410, almost being at the level of the autoregressive, and in ImageNet actually outperforming it. This darker thing here, it simply means that you average across different maskings of BERT, because I guess even in classification, it's not entirely clear how to get a signal out of BERT, because they don't do this CLS vector with BERT. What they do for classification and linear probing, and that's written up here, they simply they do an average pooling. I think they do an average pooling of all the representations of the sequence. And the last thing that I've also forgotten, there's a lot of stuff, when they fine-tune, while fine-tuning, while fine-tuning, the classification loss yields reasonable downstream performance. We find empirically that the joint objective, the generative objective, and the classification objective works even better. Okay, so even when you fine-tune with this model, you have to keep the generative modeling part, the generative loss around, and then it performs even more better, more well, whatever that word is. So that's also something to think about. I think this paper right here, it kind of lays down a lot of cool things that you can think about, and it gives rise to a lot of hypotheses of how does this stuff work, why does this stuff work. I don't even think that the numbers are the most important thing. It's mostly the fact of the effects and what does it mean. Okay, so this was my take on it. It's more kind of my rant of what I find special about this paper than about the actual paper. You can look at the paper, their numbers are pretty good. On ImageNet, they do not reach the same like super duper performance as they do on CIFAR10, and I guess that's probably because they have to downscale the ImageNet images way more than they have to downscale the CIFAR10 images, because those are of course only 32 by 32. So because they have to downscale so much, they lose probably a lot of information. And I would be interested to see if there is a way to involve convolutions in this, in all of this. So to do the downscaling that in a learned manner with convolutions or something. I'm sure this has all been done already. I'm just lazy to look it up. Yeah, so I invite you to look at their blog post where they have these samples. They look pretty funny, and these full samples up here look fairly cool for what it's trained to do, and that it has no spatial awareness whatsoever. It simply uses learned position encodings. And yeah, check it out. That was it from me. Bye bye.